Welcome to This Explainer. Today, we're taking a really fascinating journey from the microscopic lines of code all the way to the massive, real-world devices we rely on literally every single day. If you've ever wondered how the tech around us just functions so flawlessly almost all of the time, well, you're in exactly the right place. We are going to unpack the rigorous, high-stakes world of embedded software testing. Okay, let's take a quick look at our roadmap for today. We'll cover why embedded testing matters, core testing methodologies, the software testing journey, real-world and specialized tests, tools of the trade, and finally, challenges and best practices.
So let's start off with a pretty high-stakes scenario. Imagine you're driving down the highway. If a crash happens, how do we actually guarantee that those critical, life-saving systems, like your airbags or your anti-lock brakes, trigger at the absolute exact millisecond they're needed? I mean, there is literally zero margin for error here. A delay of even a fraction of a second, totally unacceptable.
The answer to that lies inside embedded systems. Think of them as the invisible brains powering our world. And hey, we aren't just talking about cars here. This kind of tech is what drives critical medical devices, your everyday home appliances, and massive industrial machines, where safety, reliability, and pure precision are just absolute non-negotiable priorities.
Because of all that, embedded software testing is an absolute necessity. It's the only way we prevent malfunctions before a product ever reaches your hands. And you weren't just testing lines of code on a computer screen. You're validating exactly how that software interacts with physical processors, CPUs, and timers. You have to ensure it operates perfectly on schedule, uses the exact right amount of power, and most importantly, doesn't fail. All right, let's dive into Section 1, Core Testing Methodologies. Engineers generally tackle this from one of two main perspectives. On one side, you've got black box testing. This is where you basically treat the system like a totally mysterious box. You ignore the internal code logic entirely, and you just provide inputs to see if the external outputs behave the way they're supposed to. But on the flip side, we have white box testing. Now this requires deep code knowledge. You're actually opening up the system to validate its internal workings, the logic, the data flow, and ensuring you get maximum code coverage.
Now, a real game changer in this field is hardware in the loop, or HIL for short. It solves a massive engineering gap. So instead of testing software in a vacuum, HIL connects actual physical hardware components to a highly simulated real-world environment. It literally feeds the software simulated digital and analog sensor inputs. This allows for incredibly intense and accurate validation way before a full physical prototype is even built. It's super cool.
Moving right along to Section 2, the software testing journey. So, this journey typically happens in three logical steps. We start microscopic and expand outward. Step 1 is unit testing. This is where we isolate tiny individual blocks of code just to ensure they work all on their own. Next up is integration testing. Here, we connect those isolated blocks to other software or hardware components to make sure they're actually communicating correctly. And finally, we reach system testing, which is where the fully integrated product gets tested under real-world conditions. The whole shebang. As you can imagine, as the scope widens at each phase, the testing tactics have to change too. During unit testing, engineers use techniques like mocking and stubbing to isolate functions and catch defects super early. Then, in integration testing, the focus really shifts over to data flow and point-to-point protocol checks between the hardware and the software. By the time we hit system testing, we're looking at end-to-end performance and testing those extreme boundary limits. And culminating all of this is regression testing. This is an absolutely vital step where previous tests are run all over again just to ensure that any new bug fixes haven't accidentally broken features that were already working.
Okay, let's jump into Section 3, real-world and specialized tests. This is where we see the transition from the lab out into the living room. Alpha testing is all about strict internal validation in a highly controlled environment. Think of testing a car's engine control unit on a simulator, right? The real-world risk is simply too high to test it anywhere else. Beta testing, on the other hand, is external validation by actual users. So imagine a smart Wi-Fi thermostat being given to a select group of customers so they can report on real-world usability, temperature variations, and, their actual network connectivity.
Now, when it comes to stress testing, the entire goal is to deliberately push these systems far, far beyond their normal operational limits. I mean, we really want to see how the software behaves when it's just hammered with extreme conditions, like heavy traffic, or when it's completely starved for resources, operating under super low memory or severe power constraints. Doing this helps identify the absolute breaking points, so engineers can fortify the system's robustness way before it ever has a chance to fail in the field.
And because embedded systems are just so incredibly diverse, engineers have to deploy some highly specialized protocols. For instance, performance testing optimizes CPU and memory usage for different types of loads. Safety testing involves failure mode analysis, basically checking exactly what happens if there's a short circuit. Real-time testing measures latency to guarantee there is zero unacceptable delay. Then there's security testing, which uses penetration checks to protect data integrity against cyber attacks. And of course, compatibility testing, which guarantees that the software works seamlessly across different platforms and remains backward compatible.
Next up, Section 4, Tools of the Trade.
To actually pull off all these complex protocols, the industry relies on a suite of really modern powerhouse solutions. Vector Kanoa is pretty much the go-to for simulating and analyzing automotive ECU networks. Then you have DSpace, which is an absolute necessity for that hardware-in-the-loop simulation we were geeking out over earlier. For continuous integration and for running automated test scripts around the clock, engineers rely heavily on Jenkins. And for automated hardware data acquisition, LabVIEW just remains a total industry standard.
Down at the super granular code level, engineers deploy some really essential tactical tools. They'll set breakpoints to pause code execution, they'll use virtual emulators to run software even if they don't have the physical hardware yet, and they utilize debuggers on the fly. And crucially, they use logic analyzers to trace physical, electrical signals. This ensures perfect data transmission between all the different components.
All right, let's head into our final part, Section 5, Challenges and Best Practices. We'll also touch on some modern updates that are solving these issues, like the whole shift toward cloud testing. So, the industry currently faces a few major technological disadvantages and hurdles. First up is hardware dependency. Honestly, testing often just stalls simply because the physical hardware hasn't even been built yet. Then you've got real-time constraints and severe resource limitations. Embedded systems often have these incredibly tiny memory capacities, which leaves very little room to even run your advanced debugging tools. And finally, creating simulations that can accurately mimic all those messy real-world analog and digital sensor inputs, yeah, that remains an immense challenge for sure. But to solve these problems, engineers rely on some really strict best practices. They start early, analyzing requirements relentlessly before the development phase even kicks off. They automate as many repetitive testing tasks as possible to ensure super consistent results. They also leverage advanced simulated environments and, increasingly, cool new updates like cloud testing to mirror actual usage without having to wait around for physical hardware. And finally, they prioritize rigorously testing those critical safety boundaries to just guarantee total, absolute stability. When you look across all of these methodologies and tools, one absolute truth remains. Rigorous testing is literally the only thing standing between a safe, smoothly functioning device and a catastrophic hardware-software failure.
So, as we wrap up this explainer, I want to leave you with a little thought to ponder the next time you step into a car, adjust your smart thermostat, or rely on any kind of medical device. When a single line of code is what controls your life-saving brakes, is the battle for perfect software reliability ever truly finished? The reality is, it's a constant, ongoing journey of innovation. Thank you so much for joining me on this deep dive into the invisible brains powering our world.